Now, quantum mechanics. Up till now, we've been speaking and actually working on orbitals from a nascent perspective. Electrons roaming around the atom. But the electrons roam the atom in mathematical patterns. In fact, the first orbital is a sphere, and then the p orbitals are literally going as far away from the sphere as possible. And that would be low density in the center, high density at the edges. And of course, this could happen in 3 dimensions, X, Y, and Z. Now, this is something that it has only been explained and used in the past century. Do not expect that the chemistry we're doing in this course and at university is ancient. While some discoveries for materials have happened 3,000, 4,000 years ago, most of the chemistry we'll be studying will be relatively new. First, there was Planck and Einstein speaking about light, okay, and photons. So light as both matter and energy. Then we had de Broglie, who spoke about all mass, okay, moving and having a wavelength. Heisenberg and the uncertainty principle. An electron, we cannot know exactly where it is. We can either know its location or its speed, but not both. So we can't know, sorry?
Its probability.
You can detect its probability where it will be, but not exactly where it is. Because it is constantly moving at different speeds with different momentums. And then you had the Schrödinger wave equation, which you will have the pleasure of doing in mathematics for chemists, or whatever its name is right now. These are things and items you will be studying in different modules. In fact, today's lecture itself, we will possibly be studying it in different topics. But this is still a good introduction for organic chemistry. So, orbitals have a 3-dimensional shape. And you can start and compare orbitals to waves, where you have nodes, where you have 0 probability of something being there, you have positives and negatives. And these are signs. These will be more obvious to why we give them notations of plus and minus later on today. But just like waves, they can have low frequencies, high frequencies, low amplitudes, high amplitudes. And just like waves, we can add them together. Okay? Now, the s orbital is a sphere. I think we all know that an s orbital is a sphere. And in fact, this acts like a mini shell. In fact, if you go from beryllium to boron, there is a decrease in energy. And this decrease in energy happens because there is some extra shielding from the s orbital. The p orbital, on the other hand, is the spherical figure of 8, and we can give this a notation of plus and minus. Okay? Whereas the s orbitals normally, we do write them either as a plus or as a minus. Okay? It's one or the other. And then we tend to write these as 1s, 2s. Now we are dividing the p orbitals in 3, the px, py, and pz. It's not bad if you write it as 2p6, but dividing the orbitals into suborbitals will help you later on. Yes? I think it is on. Now, so the s orbital, okay, the s orbital, you'll normally have the 1s being positive, 2s being negative, 3s being positive, so on and so forth. And they change sign as the shells increase. I think I switched this on. I switched something on. Whereas the p orbitals, they're a bit more complex, with having one node being plus, the other being minus. These are very, very important, okay? Because this will give us different bondings and it will give us different stabilities. The next shell, if you go into the d orbitals,
Sir,
yes,
but what does it mean when you say they're positive and negative? It means that one node
they
has
are
more electrons than the
notations we
other.
give. They are notations we give for what we're going to be doing next. Okay? So we give
Okay.
them a plus or a minus as a sign
So it's not a
for us
charge.
to know how they're going to mix. Okay? A plus with a plus will add. A minus with a minus will add. But a plus with a minus will cancel. Give me 5 minutes. If you still don't
Okay.
understand it, ask.
All right, okay. Thank you.
Okay, thank you, Caroline. Now, for the d orbitals, for now, let's leave them. So normally we start filling up electrons using the Aufbau principle, where you have an energy diagram and we fill the lower energy orbitals first. Once we get to an energy level that is the same, the px, py, pz, they are all degenerate, we will fill an electron each. Degenerate meaning they have the same energies. At this point, we must use Hund's rule, where I will fill the electrons in each orbital first, and then I start pairing them up. But first, you have the electrons as one shell, then you start adding them up. And here we can see the orbitals, okay, for 1s, 2s, 2p, 3s, 3p, 4s, 3d. Now, this is all about the energy levels. But please remember, and I'm pretty sure you're going to be doing this in an organic, that 4s is in the fourth shell. Therefore, if you need to lose electrons, the 4s orbitals will be the first to be lost. And you fill them up. So up till now, this is nothing new compared to what you've done at OA level. Sorry, not O level. But now we can have bonding. So you are going to overlap two atomic orbitals. These can be either in phase or out of phase. Now, in phase meaning that you have, so let's recall we've given the p orbitals a plus and a minus. Okay? We've given the p orbitals a plus and a minus. So, if the plus overlaps with a plus, there will be a bigger peak. Okay? A bigger amplitude. If the minus overlaps with a plus, they will be a smaller amplitude, but they will pretty much cancel out. Yes? So these are the nodes in orbitals. S, P, D, Now we're going to be speaking only about S and P. Okay? Because S is also going to be plus or minus. So this can interact with that, or it can interact with this. هنعملوها في السلايد of Naily Miss. Now, if they are in phase, this is called bonding. And things that are in phase will have a lower energy. If they are out of phase, they are the antibonding, and they will require more energy to produce.
Sir,
Yes?
by in phase, do you mean a plus bonds with a plus?
Yes,
Okay, thank you. And so the out of phase would be a plus and a minus.
exactly.
Thank you.
Perfect. So you can have a plus with a plus, okay, such as in hydrogen, okay, or a plus with a minus. And you will end up creating, so you start with two 1s orbitals. The bonding orbital, when they are in phase, the energy goes down. For the antibonding, the energy goes up. And therefore, you will always prefer items that are in phase. Whenever you have orbital overlap, you will always use items that are in phase. On the other hand, if you have extra electrons and they end up going into the anti-bonding orbital, you will start getting things that are unstable. I'm pretty sure you will be doing this more in an organic, especially for something like O2, to explain why O2 is quite reactive. Okay? But for organic chemistry, just know that bonding is stable and the bonding is not stable.
Sir, sorry. What did you mean by antibonding? Was it the
So-
out of phase?
Antibonding is the ones that are out of phase.
Okay, thank you.
Yes? So, do you remember the hybridization? We're going to be doing it soon. Hybridization, you have a number of orbitals being formed. So when you mix two orbitals, 1s and 1s, you need to have two orbitals being produced. 1, 2. Agreed? Now, these also have to have the same overall average energy. And the average would be in between them. As well as this, okay, as well as this, the bonding is where the electrons will pair up. And the antibonding orbital is normally free. If you have an electron going to the antibonding orbital, there is an unstable product, nearly always. Always, because exceptions in chemistry, they are always present, nearly always. So if you have two electrons, we're going to put them 1, 2. Okay? So let's say you bonded hydrogen, right? You bonded the electrons and you ended up getting 1 electron each. These are going to bond so that you have filled the bonding orbital. Then the antibonding orbital is empty. Okay? Wait, the lecture is being recorded, huh? So you can hear it afterwards. So, for example, H2 and HE2. Which one of these exists? H2. Okay, let's see why. So when H2 is produced, you have 2 electrons in the bonding orbitals and 0 in the antibonding orbital. Therefore, this is a stable compound. On the other hand, if you have something like He2, you have filled the bonding orbital, which we are happy to do. But you have also ended up filling the anti-bonding orbital. And at this point, you have an unstable compound, an unstable molecule. And therefore, that does not happen. Okay? Yes? At this point, it's not about the repulsion because there are plenty of molecules that have 4 electrons or more. Okay? This is about the stability of the orbitals being formed. Okay? This will be more stable for both atoms to exist individually rather than to exist as a molecule. Remember, in chemistry, every single reaction needs to have a lower energy. Okay? You need to have a lower energy. Yes?
Can you have a filled antibonding orbital and an unfilled bonding molecular orbital if it contains?
No, because you always fill the lowest energies first. For those at home, the question was, can you fill the antibonding first and have an unfilled bonding orbital? You will always fill the lowest energy levels first. Okay? And you can have plenty of different overlaps. You can have 1s with 1s. You can have a sigma bond between an s orbital and the p orbital. You can have a sigma bond between a p orbital and the p orbital. Whereas it is from 2 and 2, such as in fluorine, or 2p and 3p like fluorine and chlorine. In something like fluorine and chlorine, please note that the 2p from the chlorine will still be present. And if the 3p is positive, the 2p must have been negative. Remember, like we said for the s orbitals, when you go up a shell, we tend to give a different sign to the orbital or to the node. We do this so we know what's being overlapped and not. Please note, these plus and minus are signs, not charges. So we're not saying that here you have a plus and here the other side you have a negative sign, a negative charge, apologies. It is just a sign. It's for us to know what's mixing and not mixing. These together will form a bonding orbital.
So we're just labeling.
Yes, we're just putting a label. Yes?
Allora biex forma bond rridu jkunu phase bil-force.
To form a bond, they have to be in phase. Yes. I'm pretty sure there are not exceptions. There are some molecules that might have antibonding. I might check for next week, okay? But they would be very reactive. Yes? Yes, negative will interact with negative. If they are the same, whether they're positive and positive, negative and negative, they will still interact. Any questions from students at home?
Yeah.
Yeah.
Oh, go.
Okay, thank you. Fid-diagram tal-slide ta' qabel, kien hemm biċċa fejn il-helium ma kien iktar stabbli bħala single atoms minħabba li kien hemm l-antibonding. Issa jekk
Mela.
jinserta illi tibda binqas electrons milli jippermettu li jsir antibonding. Pereżempju jekk ikollok alpha particles fejn il-helium ħajkun positively charged. Huwa possibbli li tifforma bond hekk jew le?
So if you have He2 plus, that should be possible to form a bond. Because you remove these two electrons. So Nikolai asked, is there a way how to make He2 stable? So if I remove the electrons, two electrons, I remove the antibonding electrons, okay? So I start with He plus, that should be stable. So He2 plus should be stable. For the intent of organic chemistry, let's not go into it though, Nikolai, because here we don't really care about ions for inorganic chemicals for now. Okay? We leave that for Baish or Sonagra.
Okay. Thank you.
Kellek mistoqsija jen?
Yes, would the F and Cl bond be feasible? No, get back there.
This one?
Yes.
So of course, FCl bond is feasible. It's also very reactive.
Okay, thank you.
It's reactive not because of the bonding and antibonding, but the electronegativity difference between fluorine and chlorine is 1.2. So that would be a very electronegative molecule. And it would react very easily.
Okay, thank you.
Okay? Apart from sigma bonds, we can also have pi bonds. Okay? And pi bonds will be the overlap of p orbitals. And even at A level, we used to mention pi bonds as the overlap of p orbitals. Okay? Yes? So the 1s orbital, okay, when you mix H2, H2 would have bonding and antibonding. Okay, but the 1s itself, we normally give it a positive sign. Yes? So a pi bond is always overlap of p orbitals. Always. Sigma bond could be sigma with p with p, could be p with d. We don't go into them here. Okay? But a pi bond is always overlap of p orbitals. So, yes, the pi bond, this is the nuclei, right? The pi bond is going to be over and above. You have two sides of overlap. Whereas a sigma bond, you only have one side of overlap. Okay? Now, hybridization. So, hybridization is something that for A level you've done because of VSCPR, the valence shell electron pair repulsion theory. And this shows that any molecule or any compound where you're going to have the angles being the same, there must be a hybridization. Because let's say you have BeH2. Okay? BeH2 needs to have 1s2 and 2s2 being filled up. So you've got that. Now, this is something that you can't just fill an s orbital and the p orbital, because Okay. Apologies, I hit a button on my laptop, it seems. So you can't have a p orbital and an s orbital overlap because the bonds will not be the same. And the one thing we've learned at A level is that for any reaction, for any compound formed, the bonds must be identical so that they will be equivalent. Otherwise, you'll have a site of attack that should not exist. So I can't overlap an s orbital from the p, from the BE, and the p orbital from BE, because this shape is clearly wrong. So what happens? The orbitals will hybridize. Okay? It is the intraatomic overlap to generate two or more hybrid molecular orbitals. And in this case, this will form a linear arrangement. So hybridization would be the mixing of two or more orbitals to create the equivalent amount. So if you start with 2, you end up with 2. You start with 3, you end up with 3. 4 with 4, so on and so forth. You do not need to simply mix p and s orbitals. There are also hybridizations including the s, p, d orbitals. Okay? S, p, d orbitals. Now, so in BH2, what you'll end up getting is you form a hybrid, okay? And it will be this hybrid that will react. You form a hybrid, and it will be this hybrid that will react. So let's look at the possibilities for beryllium and why we have the shape that we have for the SP, SP2, and SP3 hybrids. So here you will have, where they are both plus, they are in phase, right? So this will increase. Where you have a plus and a minus, they are out of phase. So this will decrease. And you will get the shape that we are normally used to for hybridization. Of course, hybridization requires energy. So the hybridization itself requires energy. It is the bonding then that makes it feasible. Once they bond, it will release energy. What this means is, and its importance, is because the atoms are unhybridized, and yet once they react, they will always form a hybridized compound. Okay? The individual atoms are unhybridized. It is the product that would be a hybridized orbital. And here you have the energy diagram of the products. Now, the energy diagram, again, you should have done at A level. Now, in this course, we're always going to start from A level and then add something new. I hate trying to start materials and telling you, you should know this, therefore, let's move on. We will revise. For those who maybe did not get a D in chemistry, please do revise the topics that I had mentioned before, okay? I will help you. So anyone who will ask for my help, I will help you. So please do make sure that we will work together so that I think today you are around 40 students, all 40 students will go to second year. Or at least they will pass the subject and then it will be your choice. Now, there are other combinations that are possible. You do not just have to mix an S and a P. You can mix an S and two P's. and three-piece to give trigonal shapes and tetrahedral shapes. So if you have boron trihydride, you have two p orbitals, you have one s orbital, and you'll end up getting this mix here. Realize again, it's the same thing as before. Pluses will interact with the pluses, minuses will interact with the minuses. And this will give you three nodes where there can be overlap with the hydrogen. In the case of methane, same thing. Yes?
Fil-każ ta' beryllium hydride.
Beryllium.
Il-beryllium. Fl-A-level konna semmejna li huwa kapaċi joħloq polymer. Hemmhekk xi qed jiġri.
Mela. BH2 can form polymers, not in the merits of this course. Beryllium and group 2 elements you will be studying in a lot more detail in an organic chemistry with different lecturers. Okay, here we are just speaking about the hybridization. What happens with the p orbitals and what happens with such compounds that is not in the merits of this unit. The merits of this unit is to understand what hybridization is so that we will know how the charges can separate, we can work with resonance forms, and then we can understand what the reactions are. Okay? So
Okay.
don't worry, don't go into the merits of polymerization of these compounds. Remember, bis hawnhekk you are saying that beryllium hydride is covalent, fully covalent, which it is not. And again, here we end up having 4 orbitals because of the out of phase and in phase mixing. So here we are not creating 4 individual orbitals and adding them together. We are just mixing 3 p orbitals, 1 s orbitals, and we end up with that shape. Okay, please do understand that. Okay, please do understand that. Now, you don't just need to mix hydrogen to whatever orbital you've got. You can mix any other orbital. Someone asked me, with p orbitals, what will you get? sp3 and sp3. And that will also make a bond. Okay? So you can mix an unhybridized p orbital there. You can mix an s orbital. In some cases, you might mix a d orbital. You can mix whichever orbital your heart desires, as long as it's acceptable for the final product to share those electrons. Now, the most common that we're going to be using, ammonia and water. Remember, there's repulsion between lone pairs, okay? Therefore, they will push the electrons of the bonds closer to each other. For ammonia, this is 107.3, whereas for water it's 104.5. Now, these angles, you are expected to know them for university. At A level, we used to say 2 degrees less, okay? For A level, the exact number is better. And in triple bonds or double bonds, you will also have the overlap of the orbitals. And this is why you need to have, for example, a plus and a minus. So you have complete overlap both from both the top and the bottom. Okay? Same thing with alkynes. Together. And together. I don't mind when you draw these if you bridge them like this. I know that for A level, some students used to draw them as one thing, okay, and used to bridge them. I personally prefer to draw them with a line in them, the line bridging rather than a full cloud, because that's not what's really happening, okay? You're not really making a big bridge. This is what we're seeing because we're trying to visualize them on paper. Now, molecular models. And I will stop here because then I'm going to speak a little bit about the tests. Okay? And I normally love finishing off 5-10 minutes before so that you can go for your next lecture. Okay? Or you can take a little bit of a break before whatever you want to do next. Molecular models. I know these are expensive. Very expensive. A good molecular kit set might cost over 100 euros. But a bit of plasticine and toothpicks might cost less than 5 euros. I'm saying this because it will help you. And in my exam, and I'm going to speak about the exam here, having such a set will probably gain you 5 to 10 extra marks for sure. Possibly even more. Literally, some plasticine, if you want to go even cheaper, blue tack, okay, and toothpicks, because we are going to be doing chiral compounds, and chirality, you have to visualize it. I, for one, am not an artistic person. Drawing a human, I draw it like this. And that's a good human for me. But when it comes to organic structures, you have to draw them correctly every single time, and you have to be able to visualize what is in front of you, what is on the other side, what is on the page. If you can't do that, then there will be a bit of a problem. Because next lesson, we're going to start speaking about how to draw molecules, okay? Not all of these are acceptable for an exam. Depends on what I ask you. If I want a proper structure, normally I ask for those. Sorry, which one? Yes. Issa, if you're writing a reaction, ħafna drabi tużaw dawithom. But if I want to see the angles, if I want to see charge separation, that would help. Di kważi qatt ma ntilkom. That is too simplistic for organic chemistry. Okay? Ma jfissirx li mhux ħanamluhom. Issa l-ġimgħa d-dieħla nitkellmu ftit iktar fuqhom. And eventually, this is what I want. But of course, if these were 4 different groups, changing those groups between each other, so rotating the bond, would be a big problem. That's why we use molecular models. Again, molecular models online. I had bought one for around 30 euros, but it's small. It's a small scale. So you can only use it for one structure at a time, maybe 2. I would go and at least see what's available, or at least get creative at home. You can always. You can try. Me personally, with students at home, I tend to use plasticine. Okay, I have around 6 or 7 colors. so they can be different groups, and it helps them visualize them. Okay, I'm gonna stop the recording here.